Dear friends, in the last lecture we have discussed about the various aspects of process management, that means process address space, process abstraction, resource abstraction, process hierarchy and threads model. In this lecture we will discuss about various aspects of process scheduling and CPU scheduling. Scheduling. Multiprogramming is used to increase the productivity of the system, but it makes the working of operating system complex. Every time operating system has to decide which service is to perform for which process, so that all the resources can be used efficiently, providing services to all the processes. The decision technique used by operating system to allocate resources among competing processes is called scheduling, and the part of operating system which performs scheduling is called scheduler. The major objectives of scheduling are enforcement of fairness in allocating resources to processes, enforcement of priorities, make best use of available system resources, give preference to processes holding key resources, give preference to processes exhibiting good behavior, and degrade gracefully under heavy loads. Every process contains input output statements and executable statements. A set of consecutive input output statements is called input output burst, and a set of consecutive executable statements is called CPU burst. Generally, one process contains many alternate CPU bursts and input output bursts as shown in figure. Normally, in each process there are a large number of short CPU bursts and small number of long CPU bursts. Due to this, CPU serves all CPU bursts very quickly and effectively distribute itself among many competing processes. In this process, whenever CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. The part of operating system which performs this selection activity is called short term scheduler or CPU scheduler. Therefore, whenever CPU becomes free, CPU scheduler selects one job from ready queue on the basis of many strategies as discussed next, and allocates the CPU to that process. If any process has long CPU bursts and small input output bursts, it is called CPU bound process, but if a process has short CPU bursts and long input output bursts, it is called input output bound process. As shown in this figure, process A is CPU bound process and process B is input output bound process. Scheduling queues. As we have already discussed that a system has limited resources, for example, single CPU, single printer, etc., multiple running processes may demand for one particular resource concurrently. If the resource is free, it is allocated to one of the demanding processes, and other processes make a queue to wait for the resource to be free. If the resource is not free, all the demanding processes make a queue. There can be many queues in a system due to this waiting activity. The various queues in system are: first is job queue. Set of all programs in the system is maintained in job queue. Job queue is normally maintained on mass storage devices such as hard disk. Second is ready queue. This queue contains all the processes residing in main memory, and all the processes in ready queue are waiting for the CPU to be allocated. Third is device queues. A system may have many input output devices attached to it. If some input output device is exclusively used by one process at a time, then other processes will have to wait for that input output device to get free. The queue of processes waiting for a particular input output device is called a device queue. There can be many device queues in a system, since each device has its own device queue. In its lifetime, a process migrates between these queues. There is only one job queue and one ready queue in a system, but multiple device queues. These queues are maintained as linked list containing PCBs of waiting processes in the system as shown in figure. One can see that there is only one ready queue containing two processes P7 and P2, one device queue for magnetic tape 0 containing no process, one device queue for magnetic tape 1 containing no process, one device queue for disk unit 0 containing 3 processes P3, P14 and P6, and one device queue for terminal unit 0 containing one process P5. Next, we are going to discuss various types of schedulers. A process migrates between the various scheduling queues during its lifetime. One part of the operating system selects processes from these queues in some fashion for further processing. This part of the operating system is called scheduler. There can be three types of schedulers in an operating system as discussed. First is short term scheduler, also known as CPU scheduler. It selects one process from among the processes in memory that are ready to execute and allocates the CPU to one of them. When CPU becomes free, short term scheduler becomes active, selects a job from ready queue using any scheduling algorithm and assign CPU to it, thus making CPU busy again. Second is long term scheduler, also known as job scheduler. Selects which processes should be brought into the ready queue from job queue. When some processes terminates, only then long term scheduler is invoked to bring a new process in ready queue. Third is medium term scheduler. Sometimes when system has high degree of multiprogramming and causing frequent context switching among processes, it is beneficial to remove some of the partially executed processes from memory back to hard disk. Medium term scheduler is a program which decides when and which process to swap out or swap in from or to the memory. When degree of multiprogramming becomes less, that means some processes terminates and system resources are available, medium term scheduler swaps in partially executed processes for further execution. Short term scheduler works more frequently than long term scheduler. Degree of multiprogramming, that means number of processes in memory, is controlled by long term scheduler. Long term scheduler maintains proper mixture of CPU bound and input output bound processes to use resources more efficiently. Long term scheduler may be absent on some systems, but short term scheduler is always present. Next topic is context switch. The context switching is an activity which switches CPU from one process to another. Whenever an executing process leaves CPU, its process control block is created and the process control block of another process selected by short term scheduler from ready queue is loaded and CPU starts executing it. This whole activity is called context switching. Context switching requires processor time, and during the context switching CPU does not perform any useful task. Therefore, context switching is a pure overhead. Next we have scheduling and optimization criteria. CPU scheduler selects one process from ready queue for further execution. There are a number of scheduling algorithms for this selection, but before selecting or developing any algorithm, we should consider following scheduling and optimization criteria. First is CPU utilization. We must select the scheduling algorithm which makes CPU busy most of the time. Keeping the CPU and other resources as busy as possible is highly required to increase the utilization of system. Second is throughput. Greater the throughput, better is the scheduling algorithm. Any scheduling algorithm should complete maximum number of jobs per unit time. Third is turnaround time. Amount of time to execute and complete a particular process from its entry point is called turnaround time. It is the sum of total time taken by a process to execute, time of staying in ready queue, and time spent in waiting state. It is highly required that turnaround time should be less. Fourth one is waiting time. Amount of time a process has to wait in the ready queue is called waiting time of that process. Waiting time should be minimum for maximum utilization of resources. Last is response time. Response time is very useful criteria for interactive environment like time sharing systems. It is the amount of time taken by a process from when a request was submitted until the first response is produced. It is highly desirable that response time should be minimum. Next we are going to discuss preemptive and non-preemptive scheduling strategies. CPU scheduling decisions may take place when a process first switches from running state to waiting state, or switches from running state to ready state, or switches from waiting to ready, or terminates. The scheduling under condition 1 and 4 is called non-preemptive scheduling. All other scheduling is preemptive. Non-preemptive scheduling: once CPU has been allocated to a process, the process keeps the CPU until process terminates or process switches to waiting state. In non-preemptive scheduling, even if a high priority process becomes ready for execution, it will have to wait until the currently running process releases CPU voluntarily. In this case, CPU cannot be released forcefully from currently running process. Preemptive scheduling: in preemptive scheduling, a currently running process can be interrupted and forcefully made to release the CPU to run some high priority process, or due to some other reason like time quantum expires. Preemptive scheduling may cause inconsistency if different processes are sharing data. One example of it is a case of two processes sharing data. When one process was in the middle of updating the shared data, it is preempted to run other process. The other process may try to read the shared data which may be in inconsistent state at that moment. Next we are going to discuss various scheduling algorithms. As we have already discussed, CPU scheduling deals with the problem of deciding which process from ready queue is to be allocated to CPU. There are many scheduling algorithms as discussed below one by one. First algorithm is first come first serve scheduling algorithm. This is the simplest scheduling algorithm. Using this strategy, a process is served first, which has demanded the CPU first. In this scheduling strategy, the process which joins the ready queue first will be served first. First come first serve is a non-preemptive scheduling algorithm. Although FCFS is simplest scheduling algorithm and it treats all the processes equally, it is not suitable for executing interactive processes. The average waiting time and average turnaround time in FCFS algorithm is quite long. As shown in figure, let we have 3 processes P1, P2 and P3 having burst time of 24, 3 and 3 milliseconds respectively. The Gantt chart and average waiting time has been shown in this figure. But if the arrival sequence of these processes changes to P2, P3 and P1 as shown in this next figure, the average waiting time decreases drastically. This is called Convo effect, in which other processes wait for long time for completion of a CPU bound process. Second scheduling algorithm is shortest job first algorithm. In this scheduling algorithm, CPU scheduler selects the job from ready queue having the minimum CPU burst time. A job having minimum CPU burst is called shortest job. Hence, this algorithm is called shortest job first algorithm. If two processes have same CPU burst time, first come first serve strategy is used for them. This is the optimal algorithm. One problem with this algorithm is that it requires estimated CPU burst of each process in advance. This algorithm can be preemptive or non-preemptive. In a non-preemptive shortest job first algorithm, once CPU is allocated to a process, it cannot be preempted until the process completes its CPU burst. While in preemptive version of this algorithm, if a new process arrives with CPU burst less than remaining CPU burst time of currently executing process, the currently executing process is preempted. The preemptive version of shortest job first is also known as the shortest remaining time first algorithm. In this figure, we have shown the non-preemptive version of the SJF algorithm. Here, we have 4 processes with their arrival time and CPU bursts. Non-preemptive SJF algorithm selects the shortest jobs one by one. Average waiting time has also been calculated. In this next figure, the preemptive version of the shortest job first algorithm has shown using same set of processes. Here, if the CPU burst time of some incoming process is less than the remaining CPU burst of currently executing process, then currently executing process is preempted and incoming process is executed as P1 has been preempted after 2 milliseconds. Third algorithm is priority scheduling algorithm. Normally, a priority is associated with each process. In priority scheduling, the CPU is allocated to the process with the highest priority. If two processes have same priority, first come first serve is used for them. The shortest job first algorithm is a special case of priority algorithm, where priority was the CPU bursts. Less the CPU burst, higher the priority. Priorities are assigned as numbers. Generally, lower numbers indicate higher priority. Priorities can be defined either internally or externally. Each process is assigned internal priorities by the operating system. Internal priorities can be defined on the basis of CPU time required by process, memory required by process, input output resources required, amount of time already spent in the system, etc. The external priorities are not determined by the operating system and are dependent upon external factors such as the importance of the process, financial benefits of running the process, political factors, etc. Priority scheduling can be of two types, preemptive or non-preemptive. When a process enter ready queue, its priority is compared with the currently running process. If the priority of incoming process is higher than the currently running process, the preemptive priority algorithm preempts the currently running process and recently arrived process will get CPU. In case of non-preemptive scheduling algorithm, the currently running process is not preempted and recently arrived process will wait in ready queue till CPU becomes free. In this figure, there are 5 processes with their priorities. The Gantt chart of these processes have been shown using non-preemptive priority scheduling algorithm. One of the major problem of priority scheduling algorithm is that some low priority process may have to wait indefinitely and may not get chance to run. This is called starvation. A solution to the problem of starvation is aging. Using aging, we gradually increase the priority of processes that are waiting in the system from a long time. Aging does not affect the relative priorities of the processes already present in ready queue. Next scheduling algorithm is round robin scheduling algorithm. This is a preemptive scheduling algorithm designed for time sharing systems. In this algorithm, each process is assigned a small unit of time called time quantum for using CPU. Time quantum generally varies from 10 to 100 milliseconds. The ready queue is treated as a circular queue. CPU scheduler using round robin scheduling algorithm selects one job from front of the queue and assigns it to CPU for the fixed time quantum. Now, the running job may terminate or may require some input output operations before its time quantum expires. In this case, process releases CPU voluntarily. If the currently running process does not terminate or does not require any input output operation up to expiry of its time quantum, the process will be preempted and will be inserted at the tail of the circular queue maintained in ready state, and CPU is allocated to next process in circular queue. We have shown the working of round robin algorithm in this figure. Here we have 4 processes. The processes are executing in FCFS manner using time quantum of 20 milliseconds. P1 holds CPU for its time quantum and preempted after its time quantum expires. P2 voluntarily releases CPU before its time quantum expires. The average waiting time and average turnaround time using round robin algorithm are high. The size of the time quantum affects the performance of round robin algorithm. If time quantum is small, say 1 milliseconds, each process will get its turn to run quickly, but more context switching is required, which may waste CPU time. If time quantum is large, say 50 milliseconds, the system will behave similar like normal first come first serve algorithm. In this figure, we have shown the number of context switches required for different sizes of time quantum. Next, we have multi-level queue scheduling algorithm. A system may be running many types of processes like system processes, interactive processes, interactive editing processes, batch processes and student processes, etc. The previously discussed scheduling algorithms do not differentiate processes on the basis of their nature. Multi-level queue scheduling algorithm partitions the ready queue into multiple queues. New processes entering in ready queue are assigned to any of these multiple queues depending upon the nature of the process. each queue has its own priority. When CPU becomes free, multi-level queue scheduling algorithm selects a job from highest priority queue and executes it. When all the processes from highest priority queue are processed, only then the processes from other queues will be served. The processes of any queue can be processed only when all the higher priority queues are empty. Here, each queue may have its own scheduling algorithm like FCFS, round robin or shortest job first algorithm to serve its processes. As shown in figure, ready queue has been partitioned into 5 separate queues, each having its own priority. First of all the system processes placed in the highest priority queue will be served. After that, queue containing interactive processes will be served and so on. Multi-level queue scheduling algorithm is preemptive algorithm. If a system process enters the ready queue when CPU is serving some process from queue containing batch processes, the currently running process will preempt to make CPU to serve the system process. In last, we have multi-level feedback queue scheduling algorithm. In multi-level queue scheduling algorithm, processes are permanently assigned to any queue depending upon nature of the process. Processes from one queue cannot move to other queue. In multi-level feedback queue scheduling, ready queue is partitioned in multiple queues and each queue is assigned a priority on the basis of time slice allocated to each queue. Time quantum increases from high priority queues to low priority queues. This algorithm filters the processes on the basis of their CPU burst time. Initially, all the processes are put in the highest priority queue with a fixed and smallest time quantum. CPU serves the processes from this queue one by one in FCFS fashion. If any process releases CPU before the time quantum allocated to this queue expires, next process is served, otherwise that process is preempted and shifted to the next queue. When one queue is finished, CPU scheduler selects processes from next queue and serves each process for the time quantum allocated to that queue. Shifting of processes from this queue to further queues is done in similar fashion. In this algorithm, processes with low CPU burst are filtered from processes having high CPU burst. The working of multi-level feedback queue scheduling has been shown in figure. Initially, first queue with time quantum of 8 milliseconds contains all the processes. CPU scheduler selects processes from first queue and serves them in FCFS manner. CPU scheduler selects processes from first queue and serves them in FCFS manner. CPU serves each job for 8 milliseconds, and if CPU burst of some job is more than 8 milliseconds, it is transferred to the second queue having time quantum of 16 milliseconds. When first queue is finished, next queue is served in similar fashion by sending processes with still larger CPU burst to next queue. Finally, we have conclusions. Process scheduling is an extremely important activity for efficient utilization of resources. Schedulers are part of operating system which selects processes from various scheduling queues for further processing. The main job of all the schedulers is to implement multi-programming efficiently. There are many preemptive and non-preemptive scheduling algorithms, each having its advantages and disadvantages. Before selecting any scheduling algorithm, it is highly desirable that CPU utilization and throughput should be maximum, while turnaround time, waiting time and response time should be minimum. Thanks.